Hey, welcome back to Management Decision Tools. In this session, we're going to talk about simulation. It is not a new topic, it's been around for decades, but recent progress in computer technology, high speed and economically achievable computing cycles have made it really very insightful to work on simulated models. In the past, simulation was more along the lines of visualization. You are seeing the kind of models that we already kind of understood mathematically. But these days, when we plug the model into simulation in the way that we're going to start talking about, we actually learn some new insights in the calculations and outcomes. So in some sense, the motivation has been revived because of progress in computer technologies. So our agenda for today is very simple. We're not going to be able to perform all the complex simulated flight and games and so on, but we're going to learn something that is fundamental to all simulations in the world in some sense, and that is random number generation. We'll talk about that, right? So today idea is very simple. Let's just quickly talk about the motivation and concept behind simulation. Then we got to get to the basics of it all, and that is the random variables and a little bit on probability distribution because that's key. I really don't want to bog you down with too much statistics and mathematics, but we have to know that, the heart of it all, and that's cumulative distribution function. So we'll talk about that. And then today we're going to learn three ways to generate simulation, um, simulated numbers, random numbers, that is. All right, so we'll learn three ways to generate simulated random numbers. And then we'll end the session with a discussion of the textbook example of how a company uses simulation to make managerial decisions. So simulation is, as I said, not really something that we invented recently. It's been around. More precisely, the idea, the concept, the mathematics have been around, but not so much on getting insights in the past. So, what can we use simulation for? Um, in the past, simulation was more like a verification when we look at how the universe was created, by visualizing it. We basically kind of already knew the outcome in the past. But now, with high-speed computing power, uh, very, very affordably, we can plug in the basic know-hows that we have come to understood of a particular situation. It can be physics, pharmaceutical drug developments, climate, business, right? So it's a business part that we are more interested in talking about. So, but the idea underlying all these very disparate applications is the same. And what is the same here? In that we basically understand the component well. For example, in drugs synthesis, formulating new drugs, we may understand the underlying amino acids or the compounds and the proteins well, but when put together as a drug, is it going to be poisonous in our bloodstream or is it going to be a vitamin in our body system? So we understand the components, but we have no idea, or else it is so complex that it's not easily achievable using explicit mathematical modeling, like manual know-how calculations. It's just hard. There's no simple solution. There is no easy solution. There's no comprehensible solution. So what can we do? That's where simulation techniques come in big time. What we are doing is a bit like Lego block. We understand the geometry, the physics of individual Lego blocks, but when put together, it can be a dinosaur, it can be a house, it can be anything that is so complex, right? That we may not understand the height, the shape, the accessibility, and so on. So simulation is exactly how the technique that we use to understand and make decisions of a situation, such as a complex business merger and acquisition situation, when we understand the basics, when we understand, for example, the taxation rules, the financial implications, the calculation of interest rates, we know all these. But when put together, when many parties are involved, the government, the acquirer, the acquiree companies, the people, and so on, it is complex, right? There's no easy mathematics to talk about those, outcomes. So what can we do? So whenever we have situations where we understand the basic components well, but we do not understand how the integral system behaves when the components are put together. In such situations, and we have many, many of those, in such situations, use simulation. All right, because it is not going to just show us what we already can expect, can know, can tell in advance. No, we don't. We don't. We have no way to tell. Right, and it is able then to show us insights. It may not be telling the completely true story, right, of it all for all possible situations, but it is able to give us some insights, and sometimes, and most of the times, pretty accurate insights, so long as we know the components well enough, and we can therefore eliminate a lot of undesirable outcomes in advance. We can therefore be more prepared of possible outcomes in advance, and all those are very, very helpful. Example, we may know the behavior, the physics of air particles, all right, well, but when put together as a climate, as a behavior of the entire Earth's uh, climate system, how does it work out, right? Well, again, simulation. So, will global warming be true? We can fast forward in time, computationally, to move into the future, many decades or centuries ahead of us, and see how the Earth climate system will behave in future, right? And decide now whether we should stay on course or change our behavior. And similarly, I previously talked about the formulation of drugs, and there are, of course, games that we play on mobile phones and computers, and those are also um, simulation, because what are the components? Components will be the basic building blocks of the games, such as the players, the swords, right, the daggers, the missiles, the behavior of the monsters, the game rules, right? Like, do you have hit points? Do you have various health points, and so on and so forth, right? So individual players may have hit points and health points defined properly, but when players and monsters, and so on and so forth, when the whole system gets put together, who wins? And that is when we simulate, but of course we simulate by allowing players to have interaction, and we call that gaming, right? So uh, it is part of our lives now, so long as computer is getting cheaper and faster at economically affordable rate. Okay, so we are very motivated by this simulation, and that's how it regains its revival. Now, underlying all simulations, right? Underlying all simulations will be this one technique that is very important, and that is generation of random numbers. Random numbers. Now, by random numbers, I mean statistically random. It is not chaotically random. When it is chaotically random, it is out of control. I have really no idea what to expect next. But wait, isn't random number so random that you don't know what to expect next? Yes and no, right? Yes and no. So by random number, we are not going to generate any random number. We're going to generate random numbers that will follow a prescribed probability distribution. Okay, so what is probability distribution? Now we have to get into that. First, let's talk about what is a random variable. A random variable is like our x, y, and z in calculus, except it's not holding a constant number. It has a range of numbers, and at any one point in time, when you look at the variable, you have no idea what the value is, except a probable description. So that probable description is called the probability of the random variable having that particular value, right? All these are basics of statistics and probability. If you have done your intro classes in those topics, very good. It's a revision, and please bear with my bit of repeated explanation of those basic terms. For those of you who haven't done any of these basic introductory classes in probability and statistics, just bear with me. Only the key essence of it all that is necessary in simulation will be discussed here, right? So I'm not going to bog you down with all the details of what will be covered in a proper course of probability and statistics. So example of random variable, when we record daily temperatures, when we look at how much money we have in our pocket, when we look at how many people are there in a class, and so on and so forth. So whenever we record a value, we are basically having a random variable, all right, associated with that value. So that's just measurement, right? Think of it as measurement. Now these measured values can be discrete or continuous, right? So discrete basically means that when you record the value is always at fixed numbers. For example, when you throw a dice, the value that you record, for example, the number facing upwards, is always 1 to 6, 1, 2, 3, 4, 5, 6, and there will never be a possibility that when you throw a dice, it shows up as 1.5. Oh, you better watch it if you see 1.5, right? So that will be discrete values, and that will involve discrete distribution. Now, in many other situations, we have measurements that basically, in the abstract sense, takes up continuous values, any number in between any two numbers. So, for example, when you measure daily temperature at a place, it can be 30 degrees Celsius or 30.1 degrees Celsius or 30.05 degrees Celsius if you have the precision instruments to measure. Yeah. How about the temperature, your daily temperature, right? So because it's pandemic situation, so we have to measure daily temperature. And if you record that down, that will be a continuous random variable. So how about the price of stock, right? So the dollars and cents, although we record down to the cents, uh, abstract understanding wise, we still take it as a continuous random variable because it will assist us in making financial calculations, interest rate calculations, and so on, right? So dollars and cents always continuous distribution. Time of arrival, right? So anything to do with time, time interval, how long do you spend doing your homework, how long do you sort of allocate or actually spend actually preparing for exams. So those will be time intervals, right? And they are continuous by nature. So when we have continuous distribution, we talk about the probability distribution function. That's PDF. That's PDF. Now let's so we'll talk about that a bit more when we come to this example.